All right, we want to take a quick look at reactions and see if we can solve some of the problems or answer some of the questions that are being asked. So I'm going to work a little bit in the margins here. When I've got carbon-carbon double bonds, a lot of times I'm going to be adding something across the double bond. So in the first reaction, what I have is a carbon-carbon double bond. I'm going to add hydrogen across that double bond. So the hydrogen bond is going to break. One of the carbon-carbon bonds is going to break. The other one is going to stay intact. And I'm going to end up with a carbon-carbon single bond and a couple of carbon-hydrogen single bonds. So for this one, everything else is going to stay the same. So my carbon-based six-membered ring is going to stay the same. The carbon branches are going to stay the same. What's going to happen is hydrogen is going to be added somewhere else. Now I could write those hydrogens in, or I could leave them what's called implicit. And what I mean by that is there are hydrogens at each one of these other points along that six-membered ring that I have not drawn in, but then it's harder to see what's happened, I guess, if I don't do that. Now the other thing is, if you look at the instructions on that handout, it said that where it's possible, then this is a cis addition, which means that the hydrogens get added to the same side, which means these branches get pushed to the same side. So that wedge means they're coming out of the paper toward you rather than down into the paper or screen, I guess, away from you. It's probably not our biggest concern at this point. In number 2, I got 2 reactions, which means whatever I draw in this middle part, that's the thing that undergoes the second reaction. I need to look at the functional group. So what I have is an alkyl halide undergoing a reaction. So the carbon that was attached to the chlorine, that is the carbon that's going to be undergoing reaction. Now, I'm going to go to the margin again. We had in the list, it was a reaction that looked like this, a single carbon CH3Cl with the same aluminum chloride catalyst on that six-membered alternating double single, double single, double single six-membered ring. What that does is it put a carbon group, okay, the alternating double single stuff stayed the same, and it put the carbon group on the ring. Now what I want to do is I want to look at the bond that was broken and the bond that was formed. It was a bond between the carbon and the chlorine. Okay, think about that thing as a structural diagram. Okay, the CH3s, the H's are all bonded to the carbon is also bonded to a chlorine. It's the carbon-chlorine bond that breaks. Therefore, that's the point at which the bond forms. So looking at number 2, it's the carbon-chlorine bond that is going to be broken. And then where the bond was broken, that is where the bond is formed. So directly attached to the ring is a CH2 followed by a CH3. Everything about the ring stays intact. This is a substitution reaction, which means something out, something in. On the ring, the original ring, the thing that gets removed is a hydrogen that was written, or it wasn't written in, it was just implied, but that is removed. And if you're wondering where it went, it took off with the chlorine that was also removed. But we don't care about that stuff, so I don't draw that stuff. After that, there's a oxidation reaction. And all that happens, and it doesn't matter if there's 1 carbon, 2 carbons, 3 carbons, 5 carbons, all of them except for the one directly attached to the ring, all of those carbons get converted to carbon dioxide and bubble away, and we don't really care, so we don't write it in, but that's where all those carbons went. Reaction number 3 is an ozonolysis reaction. That's a really interesting one because it's the only one that we have that can completely break a carbon-carbon double bond. And it only breaks a carbon-carbon double bond, but it's going to break that carbon-carbon double bond, and in its place will be 2 carbon-oxygen double bonds. So to kind of think ahead or to prepare myself for this reaction, what I'm going to do is I'm going to break that bond, and where it was a carbon-carbon double bond, I'm going to make 2 carbon-oxygen double bonds. Okay. And then what I'm going to do is I'm going to start with the carbon-oxygen double bond on the left. So that's going to be a carbon-oxygen double bond. I'm going to leave the hydrogens out for a minute. I'll put those in later. And then I'm going to work my way counterclockwise. So that carbon-oxygen double bond is connected to a carbon. Going counterclockwise again, connected to another carbon. Going counterclockwise again, another carbon. That carbon is bonded to a CH3 branch, and it's bonded to another carbon that used to be a carbon-oxygen double bond on the right. Sorry, used to be a carbon-carbon double bond on the right. Now it's a carbon-oxygen double bond. Filling in the hydrogens where every carbon has 4 bonds. I need 1 on the carbon-oxygen double bond on the right, 1 on the carbon that had the branch, 2 on the carbon that used to be bottom middle, 2 on the carbon that used to be left bottom, and 1 on the carbon that used to be used to be a carbon-carbon double bond now is a new carbon-oxygen double bond. That's not the neatest looking thing ever, so what I'm going to do is I'm going to start with this and I'm going to draw it out a little nicer. So starting at one end of the chain, which is effectively the hydrogen, but actually is going to be the carbon chain, but the hydrogen to a carbon, that carbon is a double bond oxygen, followed by a CH2, followed by another CH2, followed by a CH that has a CH3 branch, followed by a carbon double bond oxygen, followed by a hydrogen. So that would be my final answer. I've gone from a ring to a chain with 2 aldehyde functional groups. In number 4, what I have is an addition reaction, so I'm going to be adding something across the double bond. I can add water as HOH or HOH. Doesn't matter to water, so I have to look at the molecule, the reactant molecule, to see if it matters there. And the preference is that the more obvious thing, so the OH or the OH, or in number 5, which is almost identical to chlorine, the more obvious looking thing is going to go to the carbon that has more carbons attached to it. Okay, so if I look at the carbon-carbon double bond in number 4, and I look at the carbon on the left, that carbon is bonded to 3 carbons in total. And if I look at the carbon on the right of the carbon-carbon double bond, that carbon has 2 carbons attached to it, or it's bonded to 2 carbons. That means the OH part is going to go to the left, and the hydrogen part is going to go to the right. And it'll be a similar story in number 5, except not an OH part. Okay, so just drawing out the carbon skeleton, the CH3 to the carbon, which is a CH3. It was going to be a carbon, it used to be a carbon-carbon double bond, now it's not, followed by a CH, CH2, CH3. Okay, so knowing that it's an addition reaction, knowing that I used that carbon-carbon double bond. The carbon that was to the left is going to get the OH. The carbon that's to the right got the hydrogen because it had fewer carbons attached to it. Now what I can do is I can draw it like that, that's no problem, or I can include that hydrogen with the hydrogen that was already there and write that as a CH2. Again, not the neatest looking thing. I could draw it a little bit neater as CH2, CH3, something like that, and then it's a little bit neater. Number 5, as I mentioned, is going to be fairly similar. Okay, hoping that worked. Otherwise, I don't know, we'll figure something out another day. Talk to you later.